that working now? Yeah, it sounds like it. Okay, thank you. Thank you very much for inviting me to this conference. It's really an honor. I have a distinct feeling of being Robin driving the Batmobile. So I'm going to talk about versality and mirror symmetry. So the aim of what I'm going to talk about is proving Konsevich's homological mirror symmetry conjecture. And I've put a list of acronyms here in case you lose track of them, because I will use them in future slides. HMS is homological mirror symmetry. There's an efficient strategy for proving HMS, which is due to Paul Seidel and was applied by him to prove it for the quartic K3 surface. And the idea is to first prove it in the large volume or large complex structure limit, and then to extend to nearby points using a versality theorem. And the main new result I'm going to describe in the talk is a general kind of streamlined version of this versality theorem that should hold in a lot of cases of interest in mirror symmetry. And applications, which I'll get to right at the end. And now that we have this versality theorem, we can prove a bunch of cases of HMS for all green Plesser mirrors, for example, which are some of the original constructions of mirror varieties, and a bunch of related examples, including one that's very interesting to lots of people, including algebraic geometers, which is Kuznetsov's K3 category of the cubic fourfold. And also an example called the Z manifold, which was of historical interest in mirror symmetry because it's rigid, which means its mirror can't be another Calabi-Yau threefold. Its mirror is a generalized Calabi-Yau. So that's kind of the payoff of proving this kind of technical result that I'll talk about. All right, and I guess the way I've decided to structure the talk is kind of going from very big picture down to more specific details of what the precise statement is. So let's start with the big picture. So if X and Y are mirror compact Calabi-Yau varieties, then mirror symmetry predicts that we should have, first thing is we should have an isomorphism between the moduli space of Kähler-forms on X, whose tangent space is H11, and the moduli space of complex structures on Y, whose tangent space is H1 of the tangent bundle of Y. And homological mirror symmetry says that the Fukaya category of X, equipped with a Kähler form corresponding to a point Q in the Kähler moduli space, should be equivalent to the derived category of Y, equipped with a complex structure corresponding to the point psi of Q in the complex moduli space. So this is really going to be a story about how these categories vary with these parameters. So what do I mean by versality and why is it useful? So first I'm going to give a simpler version of the result I'm going to talk about. And this one says, suppose we know homological mirror symmetry holds just at one point in our moduli space. It's got one point in the Q in the Kähler moduli space, one point P in the complex moduli space, and the categories are the same at those points. Well, if they're the same category, then they have the same space of formal deformations. We don't know what that space looks like, how nicely behaved it could be. But we do know one way of getting a deformation of these categories, which is to deform the geometric structure that they depend on. So we have maps like this. And now one of the very convenient things that happens is that very often these maps are actually isomorphisms. So all deformations of the category are geometric. And that implies we have these three isomorphisms. So we have an isomorphism psi between a neighborhood of Q and a neighborhood of P. And this implies that homological mirror symmetry holds at all points nearby, these ones that we started out at. But we really needed these maps to be isomorphisms. If the geometric guys were kind of like, you know, the symplectic side, the geometric guys kind of were like this, and on the complex side, the geometric guys were kind of like this, then, I mean, they might not agree anywhere other than at the point we started off at. So we really need this versal situation. But the story I'm actually going to talk about has to do with versality at points in the boundary of a compactification of the moduli space. So we can compactify the complex moduli space by allowing some degenerate varieties. And the large complex structure limit point is a zero stratum in the stratification of this compactification. It's the deepest point. In some sense, this variety, the corresponding variety, is maximally degenerate. So here's a picture of the moment polytope of CP3. In blue, we've kind of drawn a blob, which corresponds to a quartic hypersurface in CP3. And an example of a large complex structure limit is a quartic hypersurface, which is the union of the coordinate hyperplanes. So that's an example of one of these guys. We also have, on the symplectic side, we can similarly compactify our moduli space. And the way we do that is we choose a divisor D, and then we compactify the Kähler moduli space by allowing our Kähler form to become infinite along components of D. And the large volume limit is the zero stratum, the deepest kind of point in this compactification. And that's where this Kähler form has become infinite along all of D. And in particular, it kind of means that the divisor has, I don't know how you want to say, it's become infinitely far away, or it's got kind of anything passing through it has infinite energy. Anyway, we want to think of this large volume limit point as corresponding to X with this divisor removed to that symplectic manifold. So homological mirror symmetry makes sense over these boundary points in this compactification. For example, for elliptic curves, an example of a large complex structure limit elliptic curve is a nodal elliptic curve. For example, it can have just one node. And the mirror large volume limit is the elliptic curve with the divisor, which was just a point in this case, removed. And indeed, we have sensible statements of homological mirror symmetry in this case. The category of perfect complexes on the nodal elliptic curve, which is the subcategory of the category of coherent sheaves generated by locally free sheaves, that gets matched up with the Fukaya category of this punctured elliptic curve. And if you want to actually get coherent sheaves on this nodal elliptic curve, which include things supported at this singular point, which are not generated by locally free guys, then you have to look at the wrapped Fukaya category of x minus d, which includes these non-compact Lagrangians going out to the point that we removed. Okay, so makes sense to talk about homological mirror symmetry of these points. This is one example, but the other main example that you can have in mind for the rest of the talk, well, is you can imagine X being a subvariety of a toric variety and D to be the intersection of X with the toric boundary divisor. And this is another where we can study homological mirror symmetry via these kinds of ideas, and the results I'm going to talk about are really adapted to work in this generality. Okay, so let me expand on that strategy for proving homological mirror symmetry that I mentioned at the start. Again, this is due to Seidel. The idea is that it's easier to study this Fukaya category in the large volume limit. It's easier to study it after we remove this divisor. In some sense, you only need to compute a finite number of numbers to determine the category, which is kind of in contrast to the Fukaya category of the compact guy. You have a bunch of computational techniques. For example, Seidel's Lefschetz vibration techniques. If X is a fiber of an anti-canonical pencil in a Fano variety and D is the base locus, then you essentially have an algorithm for computing this category. You also have Lagrangian skeletal techniques, as originally suggested by Kontsevich and recently established, or maybe work in progress by Ganatrapad and Shende to turn that into an effective tool, and Nadler and other people. And the idea here is to study this punctured elliptic curve by contracting it down onto a Lagrangian skeleton, which is a union of two circles meeting at a point. And then one can express this Fukaya category, this wrapped Fukaya category, as global sections of some co-sheaf of categories on that skeleton, on that complex. And the other nice thing is that this category behaves nicely under taking covers and products, even when, if you put the divisor back in and compactify, these covers might no longer be unbranched, and so on. So there are a bunch of things that make it easier to compute this guy. So since it's easier to compute, it's easier for us to prove homological mirror symmetry in this limit. And then we hope that some general versality result of the kind that I mentioned before is going to allow us to extend from this boundary point in the moduli space to nearby points, which really lie in the interior of the moduli space, which is where we're really interested in proving it. Unfortunately, this space of deformations is not as simple at these points as it was in the example I mentioned before. So, first example of this, we can look at the large complex structure limit, the complex moduli space. So recall that I said an example of this was this normal crossings divisor, which is the union of coordinate hyperplanes in CP3. And we had one way of deforming this guy by smoothing it into a smooth quartic hypersurface in CP3. But there's another way of deforming it by cutting out one of these hyperplanes and gluing it back in with a twist. So we have kind of 3 C star parameters for how we choose to glue it back in along these 3 lines inside this CP2. 2 of those 3 parameters are killed by the complex torus acting on CP2, but 1 is not. So we actually have a non-trivial way of deforming this guy by re-gluing. And that gives some kind of extra component of the space of deformations of this guy. On the large volume limit, once again, at the large volume limit, it corresponds to this punctured guy where we remove the divisor. And there's one way of deforming this, the category we associate at this point, which corresponds to compactifying, putting the divisor back in and turning on a Kähler form. But there's also another way of deforming by turning on a symplectic form on X minus D. That's another way of deforming this guy as a symplectic manifold. And in general, these can give different components of the deformation space. I should say this picture is a lie because H2 of the punctured torus vanishes, so there's no space for us to turn on a symplectic form, but in higher dimensions you can have deformations like this, and we're interested in higher dimensional cases. Okay, so I've kind of described in both the symplectic and algebraic sides of the story 2 ways of deforming these guys at these boundary points. So how do we know that they're everything? How do we know, for example, that they're different components rather than just sitting inside some bigger, nice versal deformation space? Well, the way that we study deformations of an object in this case, is via, and very often, is via L-infinity algebras. So recall that an L-infinity algebra consists of a vector space with a bunch of multilinear antisymmetric operations satisfying the L-infinity relations, which I've written up there. Briefly, it says that L1 squares to 0, so it's a differential. L2 satisfies a Leibniz type rule, so it's well defined on cohomology. And the next L-infinity relation says that this L2 satisfies the Jacobi relation up to a homotopy defined by L3. So these are some kind of generalization of DG Lie algebras that might be more familiar. And given one of these guys, we can study the Mora-Cartan space. So I'm going to put this one here as well. So this is the space of solutions to the Mora-Cartan equation, which I've written there. This is something we can write for any L-infinity algebra. It's the space of solutions modulo gauge equivalence. And more precisely, we should have some kind of pro-nilpotence in the picture so that this infinite sum makes sense. Okay. This is a kind of general formalism for studying deformations of structures. So I'm going to say that the deformations of a category C are equal to the Mora-Cartan space of the Hochschild cochains on that category. And put a notice to say that it's really much more subtle than this because of how objects can appear and disappear as you vary the structure, as you vary your category. But that's not going to be important for what I talk about in the rest of the talk. So in the case of the Fukaya category, we can get a handle on these Hochschild cochains on our category, which could be some, very large dimensional thing with small cohomology, so it's kind of hard to work with. But we can get a handle on it using a certain morphism, which is called the closed-open map, and that looks like this. It maps from a certain version of Floer homology of our manifold to the Hochschild cochains on our Fukaya category. And in good situations, this map is a quasi-isomorphism, so we can study the Morikawa space of this guy, which is what we're interested in. It gives us the space of deformations of our category. If this map's a quasi-isomorphism, then it's the same as the Morikawa space of this guy, which is something more tractable that we can study. Yes. The dashed arrow means L-infinity morphism. Yeah, if I wrote a twiddle, it would be quasi-isomorphism. Okay, so what is this Floer homology that we're... It's the of the free loop space of X with respect to the action functional. It was introduced by Floer in the 80s. And it has a natural L-infinity structure that looks like what you might expect. It's a Riemann surface with a bunch of inputs and one output, giving these operations. And this L-infinity morphism CO looks like what I drew up the top there. It has a bunch of inputs coming from loops in this free loop space, and outputs are boundary conditions, giving us this Hochschild cochain. Okay, so to show you how useful this idea is, I'm going to first talk about that simpler versality result that I mentioned right at the very start, in the case where we're looking at the Fukaya category of a compact manifold. So in this case, this Floer homology localizes at the constant loops. So we have a map from X into the free loop space, just mapping point to a constant loop at that point. And this induces a quasi-isomorphism between this Floer homology and the cohomology of X. And furthermore, the L-infinity structure on that right-hand side is trivial. So that means it's really easy to work out what its Morikawa space is. It just looks like H2 of our manifold X. So any deformation of the Fukaya category comes by deforming the underlying symplectic form. So if H2 is equal to H11, like for Calabi-Yau varieties in dimension greater than 2, then we have this versality result. But in the case that we're interested in, the large volume limit, this X minus D that we're looking at is not compact, and the Floer homology we have to look at is the homology of the free loop space with respect to the action functional, which is deformed by some Hamiltonian, which goes to infinity near this divisor D. This was introduced by Floer and Hofer. And this one doesn't just come from the constant loops. it also has contributions from orbits at infinity, which link the divisor D. So because we use this kind of H that gets really big as we go out in this direction, the flow lines of the associated Hamiltonian vector field can kind of loop around the divisor D, and we get these extra generators. So in fact, there's a short exact sequence where we have a contribution coming from constant loops, which I always write in red, and a contribution coming from loops at infinity, which I'll always draw in blue. So this short exact sequence of chain complexes gives a long exact sequence like this. And it allows us to see these two ways of deforming our large volume limit point. If we deform by a symplectic form on x minus d, that corresponds to the cohomology class of the symplectic form in H2 of x minus d. And under certain conditions, these orbits at infinity correspond to, in the degree we're interested in, they correspond to H2 of x relative x minus d, where a loop going around divisor di, component I of the boundary divisor, corresponds to the class Poincare dual to that divisor di. And then if we deform x minus d by compactifying with a Kähler form omega, that corresponds to a class, which is the cohomology class of this omega, in H2 of x relative x minus d. So we see these two ways of deforming x minus d. And in fact, both of these guys, this red one and this blue one, are somehow formal L-infinity algebras, but their combination need not be. So this is the picture we have of the deformation space. We have things coming from the red guy, things coming from the blue guy. Those L-infinity algebras are simple, but then they combine and give us perhaps some extra components, some kind of stuff that we don't want to be there. What we really want is for this space of Kähler forms on X that we're interested in to be just all of the deformations and to have some versal deformation space. So what we really need is for H2 of x minus d to vanish so that we just get rid of these red and purple bits of the diagram. Unfortunately, that's just not going to happen. As soon as x is dimension 2 or bigger, I mean, in these examples, it's just not true. So what we can do to fix that is suppose that we have some group action in the picture, and suppose that the G invariant part of H2 of x minus d vanishes. And then we can look at the space of deformations that respect this action of G. So since the G invariant bad bit vanishes, that's enough for to solve this problem, to make the space of G respecting deformations versal in the way that we want. So this, although he didn't say it this way, this is very similar to what Seidel did in proving homological mirror symmetry for the cortex surface. But he used an action of a group G by holomorphisms, which is somehow, I mean, having some discrete group of symmetries of your spaces is a kind of non-generic situation. But it turns out you can also do a similar thing if you allow this group to act by anti-holomorphic involutions, which give you equivalences between your category and its opposite. In fact, in this case, where X sits inside a toric variety, you can take your group to be Z mod 2, acting by complex conjugation, and that fixes this problem for pretty much all of them. So it turns out to be very powerful to use this. Of course, if we're going to apply this idea in the way that I described to prove homological mirror symmetry, then we need this group action to exist on both sides of the story. And on the coherent sheaves side of the story, the source of natural source of equivalences between coherent sheaves and its opposite is dualizing a coherent, the functor that dualizes a coherent sheaf. Okay, so that's the outline of the idea, and now I want to state it a bit more precisely. I want to just state the theorem that I actually prove. So let me first define the Fukaya category for you. I was kind of hoping that up until now you were kind of willing to accept that this was just, you know, there's a thing that has all these properties, but now let me be specific about it. So suppose we have some compact symplectic manifold. Our category is going to be linear over the field called the universal Novikov field. It looks like formal Laurent series, except you allow real powers of the generator. The objects of this category are Lagrangian submanifolds endowed with a bit of extra structure. Morphisms are lambda vector spaces generated by intersection points. Composition maps count multilinear maps between Hom spaces that look like this. And they're defined by counting holomorphic disks U with boundary conditions on our Lagrangians like this. And the thing I really want to emphasize is that each disk U is weighted by T to the symplectic area of U. So this is an element of this field of this Novikov field in the parameter T, in the generator T. Okay, so this is the one that we're really interested in as symplectic topologists, because this is a nice, well-behaved symplectic invariant of a symplectic manifold. But in order to prove this versality theorem, we need to work with a version of this category that doesn't have such nice general properties, but that does make this versality theorem work. So we have this divisor D that's part of our data, and we introduce a coefficient ring that looks a lot like the one uses in Gromov-Witten theory, except rather than looking at closed classes, we're looking at disks which have boundary. So we look at the cone of all relative homology classes, H2 of X relative to X minus D, which pair non-negatively with any effective ample divisor supported on the divisor D. And we define our coefficient ring to be formal power series with kind of, you know, monomials in that cone. The objects we look at are certain compact Lagrangians in the complement of our divisor D, and the composition maps count holomorphic disks exactly the same as before, but now we weight a disk U by Q to the homology class of U sitting in this ring R. So this is just what you do in Gromov-Witten theory, basically. And the point of this category that I've defined is that it somehow can be thought of as a family of categories which incorporates all of the Fukaya categories of X with a symplectic form omega, where omega is spanned by the components of this divisor D. So we can think about it as a family of categories over spec of R, this coefficient ring that I just defined. It has this R has a spec of R has a point, which is the maximal ideal corresponding to the vertex of this cone of effective relative classes. And the fiber of this family of categories at this point is the Fukaya category of X minus D, which is what we expected, or what I said should happen. The large volume limit point corresponds to removing the divisor. And this is simply saying that, you know, if we set this variable q to 0, then we only count disks that never pass through the divisor. So one point in this sky corresponds to our large volume limit point. On the other hand, if we have a Kähler-form omega, it gives us a map from R to lambda, defined by this formula, which we can regard as a lambda point of spec of R, and the fiber of this family of categories over this point embeds in this Fukaya category that I said we're really interested in for symplectic topology purposes. This is, I mean, when you kind of work out what this is really saying, it's really just saying kind of Stokes's theorem that you can work out the area of a disk somehow from its relative homology class. Okay. And I should point out that this category somehow has many fewer objects than this one. This one has only Lagrangians that don't intersect D at all. And this one has any Lagrangians we like. But in many situations, you can show that the image generates this category, so that doesn't concern us. Okay. Questions? I have a feeling I might have gone through, changed gears, and then accelerated, and I don't know, not. Correct. That one is defined just over the complex numbers. I mean, and that's because this symplectic manifold is exact. The cohomology class of the symplectic form is 0, and the infinite sums of holomorphic disks whose convergence we need to ensure by using a Novikov field are actually finite if we look in the complement of D. Any other questions? I've given a talk in this conference one time before, and I finished 20 minutes early, so I don't want to do that again. But okay. I'm almost at the minus 20-minute mark, so I think I'm at least going to do better than that. Okay. So having introduced the precise definition of that category that I'm going to work with, here's the theorem that I prove. So suppose we have this group action, and the G invariant part of H2 of X minus D vanishes. So recall that was needed to rule out these extra directions of deformation. The next condition is a little technical to state. it says that D should support enough effective ample divisors. The basic point here is that the deformation argument depends on the shape of this cone of effective relative homology classes, which depends on the shape of the cone of effective ample divisors supported on D. So we need certain facts about that shape of that cone to be true for the argument to work. But in this case, as long as we work with a Kähler form that is restricted from the ambient toric variety, the theorem will work. Okay, so that's that condition. We need X to be Calabi-Yau for certain grading conditions to work out. And we want this map, this closed open map, to be surjective on the level of cohomology. And that is something that one can check is true in many cases of interest. It should be true in many cases of interest. And the conclusion is, if we have any other deformation B of the Fukaya category of X minus D over the same ring R with these effective relative homology classes, and with the same first order behavior respecting the G action, then it's basically the same as the deformation given by the relative Fukaya category, which means it's the pullback by some isomorphism or automorphism of our base space. So what this says is, if we have proved homological mirror symmetry at the large volume limit / large complex structure limit, and if we can check that the first order behaviors of our categories match up, and we have this group action in the picture, then we automatically get a mirror map between a neighborhood of the large volume limit and a neighborhood of the large complex structure limit that make homological mirror symmetry work. Okay. Any questions about the statement of this? Because I think it's not, strictly speaking, analogous to a Versality result. So I'm not saying it's a what? It's not rigid. No, it's analogous to this this result I said at the start that says, there's some space of non-trivial deformations, but it's the space is smooth, and if we have and the Fukaya category realizes all of those formal deformations of the category. So if we have some other space of deformations, some kind of inverse function theorem says that that other space is related by an isomorphism psi like this. Yes. It's this ring R that I defined. Yeah, but to explain, because I'm just getting to minus 20. So the ring R has a unique kind of toric maximal ideal corresponding to the vertex of this cone of effective relative curves. So a category over this ring, defined over this ring, whose fiber over that maximal ideal is our given one. We can call that a deformation over spec of this ring. And it's a versality result for deformations over that ring. Any other questions? just yeah, it's I'm assuming that all the morphism spaces. So you know, the way I really apply this is by looking at some specific subcategory of the categories on both sides and matching those up. And those subcategories, the morphism spaces, are just free R modules. Yeah, that's hiding a bit, and the statement is a bit inaccurate because of that. But I just didn't want to state for a specific subcategory, blah, blah, blah. It would look a bit more confusing. An analogous result holds if X is semi-positive. And if X is not semi-positive, then so far as I know, then there is no good way to rule out extra deformations which could be even more horrible than the ones these H2 of X minus D guys that I was talking about. There could be crazier deformations. Somehow the Calabi-Yau condition says that all the there are no extra graded pieces of our deformation space. There's certainly hope to have a more general versality result in cases like where X is of general type, but it's not obvious that there'll be such a clean criterion for it. I think that's all I can say. Yes. It says that one of the important things it says is there's an extra grading of this ring by H1 of X minus D. And it says that the classes corresponding to just a disk going through a single component of the divisor D should generate their graded piece of this graded ring. And in the case of toric varieties, what this condition amounts to is saying that if you have some stratum of this divisor, of, you know, an intersection of components of this divisor, any toric caliform can be supported on the other divisors, which comes from the description of toric califorms using polytopes. It follows that. Yes, it means, so we have a deformation to all orders. If we only look at, if we cut off the deformation and only look at sort of our well, what do I really mean? It means if we quotient by the square of this maximal ideal, then these two categories should be basically equivalent over this ring. Okay. So here's an application of interest to algebraic geometry people. Suppose we have a smooth cubic hypersurface. Then there's a semi-orthogonal decomposition of the derived category which has 3 exceptional objects and 1 interesting component called the Kuznetsov category, which can be regarded as some kind of non-commutative K3 surface. And the reason it's particularly interesting is that there's a conjecture that says Y is rational if and only if it is actually equivalent to the derived category of some honest K3 surface, i.e. it's not non-commutative. So there's a mirror, a putative mirror to this cubic fourfold from Batyrev-Borisov's reflexive Gorenstein-Cones construction. And the way we get it is we look at an elliptic curve with a Z mod 3 action. So this has 3, here's a picture of the fundamental domain, and the Z mod 3 action rotates by 2 pi over 3, taking this red point to this red point. So we have 3 fixed points of this group action, and we take the product with the of the elliptic curve with itself, and quotient by the anti-diagonal Z mod 3 action. And this has 9 A2 singularities, which are the images of the points Pi, Pj. So we resolve them to get a K3 surface X. So you can draw a bunch of divisors on X. Firstly, you have Pi, or the image of Pi times elliptic curve E. Secondly, you have E times image of E times fixed point Pj. And before we resolved these A2 singularities, each of these divisors would have intersected, each one on the top would have intersected the one on the bottom in one point, and those would have been the singular points. After we resolve, we introduce a bunch of exceptional curves, 2 for each of these intersection points. So I've only drawn the ones that intersect the top left guy to make the picture more comprehensible. And so there's a total of 24 divisors here. And we can define cubic monomials in variables x1, x2, x3, y1, y2, y3, corresponding to each of these divisors. xi cubed on the top, and xi squared yj, where it's this curve going from divisor I to divisor j down the bottom. Xi yj squared and yj cubed. Okay, and here is the statement of that I proved with Ivan Smith using this Versality theorem of homological mirror symmetry for the Kuznetsov category of the cubic fourfold. We suppose that we have some Kähler form on X. Its cohomology class is going to be some combination of the divisor classes that I just described. In fact, this K3 surface I described is called the most algebraic K3 surface. It has Picard rank 20, so we can actually get any Kähler form as a combination of these divisors. And then we define coefficients pk in this Novikov field for each of these divisors k. And the leading term in each of these coefficients should be t to the lambda k, where lambda k is the coefficient of the corresponding divisor in the Kähler form. That allows us to define a cubic fourfold which has leading term in its defining equation minus x1, x2, x3 minus y1, y2, y3. And then we add on one term, one multiple of each of these monomials that we defined corresponding to the divisors with the corresponding coefficient pk. So that defines a cubic fourfold in projective space over this Novikov field lambda. And the theorem we prove is that the Fukaya category of X with this Kähler form is equivalent to the Kuznetsov category of this cubic fourfold with these particular parameters pk. So I haven't actually specified them to you explicitly, but you can, in principle, write down an expression for the higher order terms. It turns out not to be important for a lot of the applications that we're interested in, so we haven't written it out yet. And the proof of this theorem goes by first proving it at the large volume, large complex structure limit point, which, by the way, this singular cubic fourfold at the large complex structure limit point means we kill all of those extra monomials and just keep those first two. And that's actually a singular toric variety, which is called the Perazzo-Primal cubic fourfold. So we prove it there, then we extend to honest Kähler forms, honest smoothings of our cubic fourfold by the Versality theorem that I stated, and that gives us the result. Okay, I'll stop there.